Tonight, we are going to travel back to the quiet moment when the first light in the universe began to move freely. We are going to witness the lifting of the cosmic fog. We are going to explore the origin of the cosmic background light. But before we drift back to the dawn of time, I invite you to subscribe to this channel and perhaps leave a comment below. Tell us where you are listening from tonight and what time it is in your part of the world. It is a small way for us to connect our own locations in space and time before we lose ourselves in the vastness of the early cosmos. Now, let your body settle. Let the gravity of the earth hold you. Let the light of your room fade, just as the light of the day has faded. We are going to a place where there is no earth, no sun, and no stars. We are going to a time when the universe was a single, glowing ocean of energy. To understand the background light, the faint glow that fills every cubic centimeter of space today, we must understand where it came from. It is not the light of stars. It is older than stars. It is the light of the universe itself. It is the afterglow of the Big Bang. We travel back 13.8 billion years. We arrive in the epoch just after the beginning. The universe has already expanded from the singularity. It has already gone through the violent burst of inflation. It has created the first matter, the quarks, the electrons, the protons, but it has not yet settled down. If you were to open your eyes in this early universe, you would see nothing, not because it is dark, but because it is too bright. You would be blinded instantly. The universe is filled with a searing, white-hot fog. It is a wall of brilliance in every direction. This fog is not made of water vapor, like the mist in a valley. It is made of plasma. Plasma is the fourth state of matter. It is what happens when you heat gas until the atoms fall apart. In our modern world, matter is polite. It keeps to itself. Atoms are neutral packages, a positively charged nucleus in the center, surrounded by a cloud of negatively charged electrons. The charges cancel each other out. The atom is electrically balanced. Because it is balanced, it does not grab onto light. Light can pass through it. That is why the air in your room is transparent. But in the early universe, the temperature is too high for politeness. It is millions of degrees. In this heat, the electrons are moving too fast to be caught. They cannot settle into orbit around the protons. They are stripped away. They run wild. So, the universe is not filled with atoms. It is filled with a soup of charged particles, protons swimming alone, electrons buzzing like angry bees, and because they are charged, they interact with everything, especially light. Light exists in this era. Photons are everywhere. They are born from the collisions of matter and antimatter. They are born from the heat of the particles. The universe is flooded with light, but the light is trapped. Imagine a photon, a tiny packet of pure energy trying to travel through this plasma. It launches forward at the speed of light, but it barely moves a fraction of a centimeter before it hits something. It hits an electron. Electrons are the enemies of free light. Because they are charged and light, they are easily pushed around by the electromagnetic field of the photon. When the photon hits the electron, it bounces off. It scatters. The photon changes direction. It tries to go left. Smack. It hits another electron. It tries to go up. Smack. Another electron. It is trapped in a game of cosmic pinball. It is a random walk. This process is called Thomson scattering. It turns the universe into a labyrinth. Even though the photon is moving at 300,000 kilometers per second, it makes no progress. It is running on a treadmill. It cannot get from point A to point B because there is no straight path. This is why the universe is opaque. Opacity is not about darkness. It is about the scattering of information. If you shine a flashlight into a glass of milk, the milk glows white. The light is inside the milk, but you cannot see through it. The light is being scattered by the fat droplets. The early universe is a cosmic glass of milk. It is a glowing, dense white fog. No image can form. No signal can travel. If there were an observer there, they would see only a uniform, featureless glow pressing against their eyes. This state of affairs lasts for a long time. Not seconds, not minutes, but thousands of years. For 380,000 years, the universe is a prison for light. Inside this prison, the pressure is immense. Light exerts pressure. It pushes against the matter. The photons are banging against the electrons, and the electrons are banging against the protons. The photon fluid and the matter fluid are locked together. They move as one. This coupling creates sound. The early universe is ringing. Gravity tries to pull the matter together. It wants to form clumps. It wants to build the seeds of galaxies. It pulls the gas inward. But as the gas compresses, it gets hotter. The pressure of the trapped light rises. The light pushes back. It blows the clump apart. This tug-of-war between gravity, pulling in, and radiation pressure, pushing out, creates waves. Sound waves. They ripple through the plasma fog like ripples in a pond. These are the baryon acoustic oscillations. They are the deepest sounds ever made. They are waves of density, moving at half the speed of light through the hot soup. They compress the gas, then rarefy it. Compress, then rarefy. These waves are crucial. They are imprinting a pattern onto the matter. They are drawing the blueprints for the future. Where the waves compress the gas, the density is slightly higher. Where they spread it out, the density is slightly lower. But the light doesn't know about the future. It only knows the trap. It is bouncing, scattering, absorbed and re-emitted over and over again. It is thermalized. This means the light settles into a perfect equilibrium with the heat of the matter. The color of the light is determined solely by the temperature of the fog. At the beginning, it is high-energy gamma rays, then X-rays. As the universe expands, the fog cools, and the light stretches into ultraviolet. But it is always trapped. We call this the photon epoch. It is the time when light ruled the universe. The energy in the photons was greater than the energy in the matter. The radiation dictated the structure of space. It is a time of frantic activity, yet on a large scale. It is a time of waiting. The universe is holding its breath. It is waiting for the temperature to drop. Thermodynamics is the clock of the cosmos. The universe is expanding, and as any gas expands, it cools. The violent energy of the Big Bang is being spread out over a larger and larger volume. The fire is dying down. Slowly, the temperature falls. Billions of degrees become millions. Millions become thousands. As the heat fades, the particles slow down. The frantic buzzing of the electrons begins to calm. They are still too fast to be caught, but they are getting tired. The protons are waiting for them. The electrical attraction between the positive proton and the negative electron is infinite in range. It is always pulling. "Come here," it says. "Join me." But for thousands of years, the heat says no. The heat gives the electron enough kinetic energy to break free of the pull. It is a dance of resistance, but the expansion is relentless. The universe gets bigger. The container grows. The heat dissipates. The balance of power is shifting. We are approaching a critical threshold, a specific temperature where the energy of the heat drops below the energy of the bond. Though, ionization energy. Imagine the universe as a room filled with steam. As long as the room is hot, the water remains a gas. The molecules are flying apart. But if you turn off the heat, eventually the room cools to 100 degrees. The steam condenses. It turns into water drops. It changes state. The universe is about to undergo a phase transition. It is about to condense, not from steam to water, but from plasma to gas, from chaos to order. This transition is the key to the story of light, because neutral gas, atoms with electrons safely tucked into their orbits, is transparent. When an electron is bound to an atom, it is restricted. It can only interact with specific colors of light. It becomes picky. It lets most of the light pass right through. But in the plasma, the electron is free. A free electron interacts with all light. It stops everything. So the entire history of the early universe is a story of waiting for the electrons to be captured, waiting for the great recombination. It is 300,000 years after the Big Bang. The temperature is now around 4,000 degrees Kelvin. It is roughly the temperature of the surface of a red dwarf star. The entire universe is glowing with a dull orange-red light. Everywhere you look, it is orange fog. There is no black sky, just orange brightness. The electrons are slowing down. They are swinging closer to the protons. They are dipping into the gravity wells of the atomic nuclei. The light is still bouncing, but the bounces are getting further apart. The density is dropping. The mean free path, the average distance a photon can travel before hitting something, is getting longer. It used to be nanometers. Now it is centimeters. Soon it will be meters. The fog is thinning. But it is not yet clear. The universe is a twilight world, a world on the brink of transparency. This era is crucial because it hides the beginning from us. When we look out into space with our telescopes, we are looking back in time. We see galaxies from 1 billion years ago. We see quasars from 12 billion years ago. But we cannot see the Big Bang itself. We cannot see the first second. Why? Because of the fog. When we try to look back past 380,000 years, we hit a wall. We hit the opaque plasma. It is like trying to look inside a cloud. You can see the surface of the cloud, but you cannot see the center. The cosmic background light we see today is the image of that wall. It is the surface of last scattering. It is the visual boundary of the universe. Behind that wall lies the mystery of the inflation, the singularity, the true origin. We can only infer what happened there. We cannot see it with light. The photons from that time never escaped. They were scrambled, absorbed, and rewritten by the fog. So, our story of light effectively begins at the wall. It begins at the moment the fog lifts. Imagine standing in that orange mist. The silence is absolute, despite the energy. The scale is infinite. There is no horizon, because there is no ground. There is only the glowing medium. You are floating in the raw material of the stars. The hydrogen nuclei around you will one day be in the heart of a sun, or in the water of an ocean, or in the strand of a DNA molecule. But for now, they are just dust in the wind of the expansion. And the light is frantic. It is desperate to leave. It carries the energy of the creation, but it has nowhere to go. It pushes against the walls of its own cage. It pushes against the electrons, keeping the matter apart. It prevents the gravity from winning. It prevents the stars from forming. As long as the light is trapped, the universe cannot evolve. It is stuck in a hot, featureless limbo. The liberation of light is the liberation of matter. Once the light leaves, matter can finally collapse. It can finally fall into the dark matter wells and build the galaxies. So the event we are approaching, recombination, is not just a light show. It is the unlocking of the future. It is the starting gun for the structure of the cosmos. In the next chapter, we will watch this event unfold. We will see the temperature drop past the critical point. We will see the electrons surrender to the protons. We will witness the clearing. We will see the universe turn from opaque to transparent in a cosmic heartbeat. We will follow the first free photons as they launch into the void, beginning a journey that will last for 13 billion years. A journey that will end, for some of them, on the mirror of a telescope on a small blue planet. But for now, stay in the warmth, stay in the fog. The universe is young, hot, and full of potential. The separation has not yet occurred. Everything is one. Light and matter are dancing together in a tight, unbreakable embrace. It is the embrace of the beginning. Rest in that unity. The clarity is coming. We have witnessed the universe as a blinding, suffocating cage of light. We have seen the photon trapped in the pinball game of the plasma, unable to move more than a microscopic distance before crashing into an electron. It is a world of static, white noise, and infinite heat. But the universe is not static. It is dynamic. It is a machine built to change. The engine of this change is expansion. From the first moment of the Big Bang, space has been stretching. And as it stretches, it performs a miracle of thermodynamics. It cools. To understand why, imagine a gas trapped inside a piston. If you pull the piston out, increasing the volume, the gas has to fill the new space. To do this, the molecules must do work. They must spend energy to push outward. As they spend this energy, they slow down. And in the world of atoms, speed is temperature. Slow atoms are cold atoms. Fast atoms are hot atoms. The universe is the ultimate piston. It is expanding in every direction at once. Every cubic centimeter of space is stretching into 2, then 4, then 8. The particles moving through this space are being diluted. The energy density is dropping. The fire is banking down. For the first few thousand years, this cooling was rapid. The temperature dropped from trillions of degrees to millions. But as the universe grew larger, the cooling slowed. It became a long, gradual slide down the thermometer. We are entering the epoch of the photon-baryon fluid. This is the technical name for the soup we described in Chapter 1. Baryon refers to normal matter, protons and neutrons. Photon refers to light. In this era, they acted like a single fluid. They were locked together by the constant collisions. Where the matter went, the light went. Where the light went, the matter went. They sloshed around the universe together, driven by gravity and pressure. Gravity tried to pull the fluid into puddles. Radiation pressure tried to blow the puddles apart. The universe was ringing like a bell, vibrating with sound waves that rippled through the glowing fog. But as the temperature drops, the balance of power begins to shift. The light is losing energy. As space expands, the wavelength of the light is stretched. It shifts from gamma rays to X-rays to ultraviolet. It becomes less violent. It pushes with less force. The matter, too, is changing. The electrons are slowing down. For hundreds of thousands of years, they have been manic, buzzing around at near light speed, refusing to be tamed. But now, as the thermometer reads 10,000 degrees, then 8,000, then 6,000, they begin to tire. They are feeling a pull they could previously ignore. The high-inch electrostatic attraction of the protons. A proton is positively charged. An electron is negatively charged. Opposites attract. They want to be together. They want to form an atom. This is the most natural state of matter. The hydrogen atom, one proton holding one electron, is the bedrock of chemistry. But heat is the enemy of the bond. If an electron gets close to a proton in a hot plasma, a high-energy photon will smash into it and knock it away. It is like trying to build a house of cards in a hurricane. The structure is destroyed as fast as it is built. This process is called ionization. So, the universe waits. It waits for the hurricane to downgrade to a storm, and then to a breeze. It waits for the photons to become weak enough that they can no longer knock the electrons out of orbit. This critical threshold is known as the ionization energy of hydrogen. It is a specific number, 13.6 electron volts. If the photons have more energy than this, atoms cannot exist. If they have less, atoms can survive. We are approaching the moment of truth. The timeline is roughly 380,000 years after the Big Bang. The temperature is hovering around 3,000 Kelvin. This is a familiar temperature. It is the temperature of the filament in a light bulb. It is the temperature of the surface of a red dwarf star. The universe glows with a dull orange-red light. It is no longer blinding white. It is the color of a dying ember. The fog is still there, you still cannot see through it, but it is dimmer. The roar of the acoustic waves is quieting. And then it happens. The Great Recombination. It does not happen instantly, like a switch being flipped. It is a phase transition, like steam turning into water. It happens in patches, then spreads. An electron, tired and slow, drifts near a proton. The proton's electric field reaches out and grabs it. The electron falls. It spirals down into the energy well of the nucleus. It snaps into place. For the first time in history, it stays there. A photon hits it, but the photon is too weak to knock it back out. The photon bounces off harmlessly, or passes right through. The bond holds. Hydrogen is born. This process repeats trillions of times across the vast expanse of the cosmos. The free electrons are swept up. The plasma is neutralized. The soup turns into gas. And in that moment of capture, something magical happens to the light. Remember why the universe was opaque. It was opaque because free electrons scatter light. They act as a fog. But neutral hydrogen atoms are different. They are picky eaters. They only absorb very specific wavelengths of light, the frequencies that correspond to the jumps between electron orbits. To almost all other wavelengths, the hydrogen atom is transparent. It is like glass. So, as the electrons are locked away in their atomic cages, the fog lifts. The barrier dissolves. The photons, which have been trapped in a random walk since the first second of time, suddenly find that the road ahead is clear. There are no more obstacles. There are no more toll booths collecting energy. The universe opens up. This event is called photon decoupling. The light and the matter, which have moved together as a single fluid for eons, divorce. They separate. Matter goes one way, to clump under gravity. Light goes the other way, to fly freely through space. Imagine being inside a thick cloud. You can see only white mist around you. Then suddenly, the cloud evaporates. You see the sky. You see the horizon. You see for miles. That is what happened to the universe. It became transparent. The light that was liberated in that moment, the first light, launched into the void. It began a journey that would last forever. This light is the cosmic background. It is a snapshot of the universe at the exact moment of clearing. It is a fossil image of the primordial plasma, frozen in time. Attachment, duo, attachment. When we look at this light today, we are looking at the surface of last scattering. This is a term used by cosmologists. It is like looking at the surface of the sun. When you look at the sun, you are seeing the layer where the gas becomes transparent. You cannot see deeper inside. The cosmic microwave background is the surface of the sun of the early universe. It is a wall of fire that surrounds us at a distance of 13.8 billion light-years. Behind that wall lies the plasma. Behind that wall lies the mystery. But the wall itself is the limit of our vision. Let us pause and consider the color of this light. At the moment of release, the universe was 3,000 Kelvin. It glowed orange. If a human could have survived in that environment, which they couldn't, and looked around, they would have seen a uniform bright orange glow in every direction. No stars, no shadows, just endless bathing luminosity. It would have been like living inside a neon tube. But as the light traveled, the universe continued to expand. And as we learned in the previous story, expansion stretches light. It redshifts it. The orange light became red, then infrared. Then, over billions of years, it stretched into microwaves, invisible, cold waves of energy. Today, that fire has cooled to 2.7 degrees above absolute zero. The searing heat has become a frigid whisper, but it is still there. It is the dominant source of radiation in the universe. There are 400 million of these ancient photons in every cubic meter of space. You are bathing in them right now. They are passing through your body, through the earth, through the walls. They are the ghosts of the Big Bang, touching you. This moment of recombination also set the stage for gravity to finally do its work. While the light was trapped, it exerted pressure. It pushed matter apart. It prevented gravity from collapsing the gas clouds into stars. It smoothed out the universe. But once the light escaped, the pressure vanished. The matter was left alone in the dark. It was cold, it was neutral, and it was heavy. Gravity, which had been waiting patiently in the wings, stepped onto the stage. It took hold of the dark matter halos. It took hold of the hydrogen gas. It began to pull. Without the radiation pressure to fight back, the gas began to fall. It flowed into the wells dug by dark matter. It began to pool. This was the beginning of structure, the beginning of galaxies. The decoupling of light allowed the universe to become lumpy. It allowed the uniform fog to break apart into islands of matter. But this structure formation would take time, a lot of time. The era immediately following recombination is a strange one. The light has gone. The stars have not yet been born. The universe plunges into the dark ages. The background glow fades into the infrared, invisible to any eye. The gas is dark. The only energy is gravity, silently pulling in the void. It is a time of gestation. The universe is pregnant with stars, but not yet delivering them. For hundreds of millions of years, the cosmos was a black sea, but hidden in that sea were ripples. Remember the sound waves, the acoustic vibrations that rang through the plasma? Those waves left fingerprints. When the universe froze at recombination, the sound waves froze too. They created regions of slightly higher density and slightly lower density. The gas was not perfectly smooth. It was curdled. These subtle variations, tiny differences in temperature and density, are preserved in the cosmic background light. When we map the light today, we see spots. We see patches that are slightly warmer by a millionth of a degree, and patches that are slightly cooler. These spots are the seeds of the galaxies. A cool spot in the CMB corresponds to a region that was slightly denser. Because it was denser, it had more gravity. Because it had more gravity, it pulled in more matter. It grew. It became a galaxy cluster. A warm spot corresponds to a region that was less dense. It emptied out. It became a cosmic void. So, when we look at the static on the TV screen or the map of the microwave sky, we are looking at the blueprint of the modern universe. We are seeing the baby photo that predicts the adult face. The fact that we can see this light at all is a miracle of timing. We live in a universe that is transparent. If the physical constants were slightly different, if the ionization energy of hydrogen were different, or if the expansion rate were different, the fog might never have lifted. We might still be living in a plasma soup. Or, if the universe were older, the light might have stretched so far that it became undetectable. We live in the perfect window to see our own origins. In the next chapter, we will follow these liberated photons on their journey. We will see how they travel through the expanding void. We will look at the obstacles they face, the gravitational lenses that bend them, the dust clouds that absorb them, and the redshift that ages them. We will explore how the universe acts as a time machine, stretching the news of the past until it becomes a whisper. For now, imagine that moment of clearing, the Great Recombination. The orange fog dissolves. The curtain rises. The infinite depth of space is revealed for the first time. The photons, joyful and free, rush out into the black, carrying the secret of the beginning to the end of time. Rest in that clarity. The confusion is gone. The path is open. You are floating in the transparent open ocean of the early cosmos. There is nothing to bump into. There is only peace and the long, straight road ahead. The fog has lifted. The great cage of the plasma epoch has dissolved. For 380,000 years, the universe was a trap for light, a dense, opaque storm of charged particles that refused to let a single photon pass. But now, the temperature has dropped. The electrons have been captured by the protons. The atoms are neutral. The silence of the vacuum has begun. In this new, transparent universe, the photons are suddenly free. They have spent eons bouncing back and forth, trapped in a microscopic prison. But now the walls are gone. The path ahead is clear. There are no obstacles. There are no scattering electrons. There is only the infinite open road of expanding space. And so they fly. Trillions upon trillions of photons, the accumulated energy of the Big Bang, launch themselves into the void simultaneously. It is the greatest release of energy in the history of time. It is the flashbulb of the cosmos going off. If you could stand in the universe at this moment, roughly 380,000 years after the beginning, what would you see? You would not see the black, starry sky of the modern night. You would see a uniform, glowing wall of light. The temperature of the gas is about 3,000 degrees Kelvin. This is the temperature of the surface of a red dwarf star, or the filament of a dim light bulb. The entire universe glows with a bright, warm, orange-red color. There are no shadows. There is no darkness. There is only this bathing, omnidirectional luminance. It is a world of pure light. If you looked up, down, left, or right, the view would be the same. You are suspended in a sea of photons. This is the first light. It is the moment the universe became visible to itself. Astronomers call this moment photon decoupling. The photons have decoupled. They have unhooked themselves from the matter. They are no longer slaves to the gas. They are independent entities traveling on their own geodesics, their own straight lines through space-time. This light moves outward in every direction. Because the universe is infinite, or at least vast beyond measure, and filled uniformly with this glowing gas, every point in space is emitting light, and every point in space is receiving light. It is a perfect equilibrium. As these photons travel, they carry a snapshot of the universe at the exact moment of their release. Imagine taking a picture of a cloud. The picture records the shape, the density, and the texture of the water vapor at the moment the shutter clicked. The first light is a photograph of the primordial universe. It records the density and temperature of the gas at the instant of recombination. It is a fossil image, frozen in energy, traveling across the eons to reach us. When we look out into the deep universe today with our radio telescopes, we are looking back in time. We see galaxies from 1 billion years ago. We see quasars from 10 billion years ago. But if we look far enough back, we hit a wall. We hit the wall of the opaque plasma. We cannot see past this wall. The universe, before recombination, is hidden from us by the fog. The first light comes from the very surface of that fog. We call this the surface of last scattering. Attachment, da'wao, attachment. It is called this because this was the last time the photons scattered off an electron. It was the last time they interacted with matter. After this last collision, they flew straight. They have been flying straight for 13.8 billion years. Think of the journey of one of these photons. It hits your detector, or perhaps the static on your old television set. Today, that photon has traveled across the entire observable universe without hitting a single thing. It has dodged galaxies. It has missed stars. It has passed through dust clouds without being absorbed. It is a pristine messenger from the deep past. It has not been touched since the universe was a baby. It carries the secrets of the beginning directly to your eye. But the light has changed during its journey. It started as visible, orange light. It was hot. It was energetic. But the universe has been expanding for all that time. And as space expands, it stretches the light waves traveling through it. We will explore the mechanics of this redshift more deeply in the next chapter, but the effect is profound. The orange light was stretched into red, then into infrared, then into the far infrared, and finally into microwaves. Microwaves are low-energy radio waves. They're cold. The 3,000-degree heat of the early universe has been diluted by the expansion until it is now only 2.7 degrees above absolute zero. The blinding wall of fire has become a faint, cold whisper, but it is still there. It is the cosmic microwave background, CMB. It fills every cubic centimeter of space. It is the dominant radiation in the universe. If you have eyes that can see microwaves, the entire sky is glowing. Day and night do not exist for the CMB. It comes from everywhere. The Earth is bathed in it. You are bathed in it. It passes through the roof of your house and through your body. It is the ghost of the Big Bang haunting the modern world. Now, let us look closely at this surface. At first glance, the surface of last scattering looks perfectly smooth. The temperature seems to be exactly the same in every direction, 2.725 Kelvin. This uniformity is amazing. It tells us that the early universe was incredibly homogeneous. It was a smooth soup. But if it were perfectly smooth, we would not be here. If the gas had been distributed perfectly evenly, gravity would have had no toehold. Every atom would be pulled equally in every direction by its neighbors. The net force would be zero. The gas would never have collapsed. No stars would have formed. The universe would be a cold, dark, boring mist forever. So, we look closer. We build better satellites, COBE, WMAP, Planck, to map the temperature of this background light with exquisite precision. We look for variations of 1 part in 100,000. And we find them. The map of the cosmic microwave background is not a flat color. It is speckled. It looks like a tie-dye shirt or the surface of a rough orange. There are spots that are slightly warmer, red, and spots that are slightly cooler, blue. These tiny fluctuations, these anisotropies, are the seeds of everything. The cooler blue spots correspond to regions where the gas was slightly denser. Because it was denser, gravity was slightly stronger. It had to work harder for the light to escape the gravitational pull, which robbed the light of a tiny bit of energy, making it look cooler to us. These dense spots are where the matter began to clump. These are the birthplaces of galaxy clusters, the Great Attractor, the Coma Cluster, the supercluster that holds the Milky Way. All of them began as a tiny blue speck on this map of the early universe. The warmer red spots correspond to regions where the gas was slightly less dense. Gravity was weaker. The light escaped easily, keeping its energy. These regions became the great voids, the vast, empty spaces that separate the filaments of the cosmic web. So, when we look at the CMB, we are looking at the blueprint of the cosmos. We are seeing the DNA of the universe before it grew up. We can trace the structure of the modern universe directly back to these microscopic ripples in the primordial plasma. Where did these ripples come from? They are the fossilized sound waves we spoke of earlier, the baryon acoustic oscillations. The ringing of the early universe compressed the gas in some places and rarefied it in others. When the universe froze at recombination, the sound waves were caught mid-oscillation. The pattern of the sound became the pattern of the matter. We are seeing music turned into galaxies. But there is another layer to this mystery. these ripples originated even earlier, in the first fraction of a second during inflation. They started as quantum fluctuations, tiny, random jitters in the fabric of space-time itself. Inflation stretched these subatomic jitters to the size of galaxies. The largest structures in the universe are just quantum mechanics writ large. The release of the photons did not just reveal this structure, it enabled it. As long as the light was trapped, it exerted pressure. It pushed the matter apart. It fought against gravity. It smoothed out the clumps. But the moment the light escaped, the pressure vanished. The scaffolding was removed. The matter was left alone in the dark, cold, and unsupported. Gravity, which had been waiting patiently, finally took control. The dense spots began to collapse in earnest. The gas flowed into the wells. The structure formation began. The release of the light was the starting gun for the construction of the material universe. But let us stay with the light itself. After recombination, the universe went dark. This sounds contradictory. We just said the universe was filled with orange light. How could it be dark? It was dark in the sense that there were no sources of light. There were no stars. There were no galaxies. The orange glow was fading. As the universe expanded, the light redshifted. It moved from visible light into the infrared. To a human eye, the sky would have slowly turned from bright orange to dull red, to deep crimson, and finally to total blackness. The Dark Ages had begun. For hundreds of millions of years, the universe was filled with invisible infrared photons drifting through invisible hydrogen gas. It was a time of waiting, a time of gestation. The light of the Big Bang was fading away, and the light of the stars had not yet ignited. It was the longest night in history, but the photons kept traveling. They flew through the dark, silent universe, witnessing the slow assembly of the first halos. They passed through the clouds of hydrogen that were slowly gathering to form the first stars. Because they were infrared, they didn't interact much with the gas. They slipped through the neutral atoms like ghosts. The universe was transparent to them. This transparency is a gift to astronomers. It means we can see all the way back. If the universe had remained a plasma, we would never be able to see the beginning. The fog would block our view. But because the fog lifted, the history of the cosmos is open to us. Imagine the sheer number of photons. In every cubic meter of space today, there are about 411 of these ancient photons. There are billions of times more photons in the universe than there are atoms. The universe is mostly light. Matter is just a trace contaminant. We live in a bath of radiation. If you tune a radio to a frequency between the stations, you can hear the hiss. That noise is the sound of the photons hitting the antenna. It is the static of creation. The discovery of this background light in 1965 by Arno Penzias and Robert Wilson was accidental. They were trying to calibrate a radio antenna in New Jersey and couldn't get rid of a persistent hum. They thought it was pigeon droppings on the dish. They cleaned it, but the hum remained. They realized the hum was coming from everywhere in the sky, day and night. They had found the echo of the Big Bang. It was the death knell for the steady-state theory of the universe. It proved that the cosmos had a hot, dense beginning. We found the smoking gun of creation in the noise of a radio. As we drift through this chapter, visualizing the surface of last scattering, Imagine it as a sphere surrounding us. No matter where you look, if you look far enough, you hit this wall. We are inside a bubble of the present, surrounded by the shell of the past. The farther out we look, the further back we see, until we see the fire. But the fire is cold now. It has been tamed by time. It washes over the earth gently. It does not burn. It informs. It carries the pattern of the seeds. It carries the promise of the galaxies. It is the bridge between the chaos of the origin and the order of the now. In the next chapter, we will follow this light as it moves through the expanding universe. We will explore the phenomenon of redshift in detail. We will see how the stretching of space acts as a time machine, slowing down distant events. We will see how the light loses energy, growing tired as it climbs out of the gravity well of the Big Bang. We will understand why the sky is dark at night, Olber's paradox, and how the expansion saves us from being roasted by the infinite starlight of an infinite universe. But for now, rest in the transparency. The fog is gone. The view is clear. The first light has been released, and it is on its way to you. You are the destination of a message sent 13 billion years ago. You are the eye that catches the ancient photon. Drift in the afterglow. The universe is open. The silence is filled with light. We have watched the galaxies drift apart, carried by the silent river of expanding space. We have seen them settle into islands, separated by growing voids. But how do we know this is happening? We cannot feel the expansion. We cannot see the galaxies moving with the naked eye. They appear frozen in the amber of the night sky. To see the motion of the universe, we must learn to read the only message that can cross the void. We must read the light. Light is not just illumination, it is information. It is a code that carries the secrets of its source, its temperature, its composition, and most importantly, its speed. To decode this message, we must understand the nature of the signal. Light travels as a wave. It is a ripple in the electromagnetic field, oscillating up and down as it flies through the vacuum. The distance between two peaks of this wave is called the wavelength. Our eyes interpret this wavelength as color. Short, tight waves are blue. Medium waves are green. Long, lazy waves are red. This is the spectrum of the rainbow. But the spectrum is fragile. It can be changed. It can be stretched. Imagine you are standing by a train track. In the distance, a train approaches, blowing its whistle. As it rushes toward you, the sound is high-pitched, a scream. The sound waves are being squashed together by the speed of the train, shortening their wavelength. But as the train passes you and speeds away, the sound drops. The scream becomes a moan. The pitch lowers. This is because the sound waves are now being stretched out behind the train. This is the Doppler effect. It applies to sound and it applies to light. Attachment. If a star moves toward us, its light waves are compressed. They turn blue. This is blue shift. If a star moves away from us, its light waves are stretched. They turn red. This is redshift. In the early 20th century, astronomers began pointing their spectroscopes, instruments that break light into rainbows, at the fuzzy nebulae in the sky. They expected to see a mix, some moving toward us, some moving away, just like gas molecules in a balloon move in random directions. But that is not what they found. When Edwin Hubble and his assistant Milton Humison analyzed the light from these distant islands, they saw red. Almost everywhere they looked, the light was shifted toward the red end of the spectrum. And it wasn't just a subtle shift. The farther away the galaxy was, the redder it appeared. A galaxy nearby might be moving away at 1,000,000 miles an hour. A galaxy twice as far away was moving at 2 million. A galaxy 3 times as far, 3 million. This was the smoking gun. This was the proof that the universe was not static. It was exploding outward. But here, we must make a crucial distinction, a distinction that is often misunderstood, but which is the key to understanding the cosmos. The galaxies are not moving through space away from us, like shrapnel from a bomb. If they were, we would be at the center of the explosion, which is statistically impossible. Instead, space itself is expanding between us. This is cosmological redshift. It is different from the Doppler effect. The Doppler shift happens when the source moves. Cosmological shift happens when the road moves. Imagine drawing a wavy line on a rubber band. The line represents a light wave. Now, stretch the rubber band. The wave gets longer. It stretches out. The peaks move further apart. The light hasn't changed its nature. The fabric it is traveling on has grown. This is what happens to a photon as it crosses the intergalactic void. It leaves a distant star as blue light. It flies for 1 billion years. During that 1 billion years, the universe expands. The space the photon is traveling through stretches, and because the photon is embedded in space, it stretches too. By the time it hits your telescope, it is red. It is tired. It has lost energy. The expansion of the universe has literally sapped the strength of the light. This tells us that the universe is a cooling engine. It is taking the high-energy fire of the Big Bang and stretching it into the low-energy chill of the deep future. But how do we know it is redshift? How do we know the star isn't just naturally red? There are red stars, after all. We know because of the barcodes. When light leaves a star, it passes through the star's atmosphere. The atoms in that atmosphere, hydrogen, helium, calcium, absorb very specific wavelengths of light. They leave dark lines in the rainbow. These are called Fraunhofer lines. These lines act as a fingerprint. Hydrogen always absorbs light at exactly the same frequencies. It creates a specific pattern of gaps, like a barcode. When Hubble looked at distant galaxies, he saw this hydrogen barcode, but it was in the wrong place. The whole pattern had been shifted to the right, toward the red. It was like sliding a stencil over a drawing. The pattern was identical, but the position had changed. This proved that the light was being stretched. The amount of this shift is represented by the letter ZAD. A zahas of 0 means no shift. A zahas of 1 means the wavelength has doubled. The universe has doubled in size since that light was emitted. We have seen galaxies with a redshift of ZAD equals 13. This means the universe has expanded by a factor of 14 since that light left its source. The light from these galaxies left them when the universe was only a toddler. It has been traveling for 13.4 billion years, stretching all the while. When it started, it was blinding ultraviolet light. Now, it arrives as invisible infrared light. We cannot see it with our eyes. We need special telescopes, like the James Webb, which are designed to see heat rather than light, to detect these ancient ghosts. This stretching has a profound consequence for how we perceive the universe. It means that the farther we look, the darker things get. The light is being diluted. Not only is it spreading out over a larger area, the inverse square law, but each individual photon is carrying less energy because of the redshift. If you could look far enough to the edge of the observable universe, the light is shifted so far that it becomes microwaves. This is the cosmic microwave background we spoke of. It is the wall of fire from the Big Bang, redshifted by a factor of 1100. The fire has become a faint hum, but redshift affects more than just color. It affects time. This is one of the most mind-bending aspects of cosmology. The expansion of space stretches the gap between events. It creates a slow-motion effect. Imagine a distant supernova. It explodes. The explosion takes, say, 20 days to fade away. It sends out a stream of photons. The first photon leaves on day 1. The last photon leaves on day 20. These photons travel toward Earth, but as they travel, space expands. The distance between the first photon and the last photon increases. They get spread out. By the time they arrive at Earth, billions of years later, the gap between them has doubled. The first photon arrives. We start our clock. We wait for the last photon. It doesn't arrive in 20 days. It arrives in 40 days. To us, looking through the telescope, the explosion seems to take twice as long as it actually did. We are watching the past in slow motion. This is cosmological time dilation. We have measured this. We watch supernovae at different distances. The further away they are, the slower they seem to explode. A standard bomb that takes 2 weeks to detonate nearby takes 4 weeks to detonate at redshift 1. At the edge of the universe, time seems to crawl. If there were a clock on a distant quasar, we would see its second hand taking minutes to tick. And they, looking back at us, would see our clocks running slow too. This is the relativity of the expanding cosmos. We are trapped in our own time bubble, and everyone else appears to be moving through molasses. This stretching applies to information too. If an alien civilization in a distant galaxy tried to send us a message, a radio broadcast, the signal would be stretched. Their high-pitched voices would become deep bass. Their rapid data stream would become a slow, lethargic pulse. Communication across the cosmos is fighting against the tide of expansion. The universe is working to isolate us, to slow down the conversation until it stops. This brings us back to the idea of the horizon. Because the expansion is accelerating due to dark energy, there is a point where the recession velocity exceeds the speed of light. Attachment 1. Attachment. Regions of space are moving away from us faster than light can travel. This does not violate Einstein's rules because it is space expanding, not objects moving. But it creates a boundary, the cosmic event horizon. Any light emitted beyond this horizon will never reach us. It is like a runner on a treadmill that is moving faster than she can run. She will be swept backward. The light is swept away into the dark. This horizon is shrinking. Or rather, more and more galaxies are crossing it, leaving our observable bubble. Every day, galaxies that we could once see drift across the line and vanish. They are disconnected from our causality. They are gone forever. We are losing the universe. Piece by piece, galaxy by galaxy, the cosmos is redshifting out of existence. Eventually, in the far future, the local group of galaxies, Milky Way and Andromeda, will be the only things left in the visible sky. All the other billions of galaxies will have been swept over the horizon. The sky will be dark, save for our own stars. Future astronomers will look up and see a static, lonely universe. They will not see the expansion. They will not see the Big Bang's afterglow, which will have stretched into undetectable radio waves. The evidence of our origins is being erased by the expansion itself. We are living in a privileged time. We live in the era where the light can still reach us. We can still read the history of the universe written in the Redshift. We can still see the echo of the beginning. Let us return to the photon's perspective. Imagine being that particle of light. You are born blue and hot. You fly through the void for eons. You feel the space around you growing. You feel your own energy stretching thin. You feel yourself relaxing, cooling, shifting to red. You are aging, but you are not dying. You are simply changing your tune. You are harmonizing with the growing universe. By the time you hit the mirror of a telescope on Earth, you are a long, gentle wave. You carry the news of a universe that was smaller, hotter, and more violent. You are a memory made of energy. This redshift is the color of deep time. When you see a photo of deep space, filled with tiny red specks, you are seeing the oldest things in existence. The redder they are, the older they are. It is a visual sorting of history. Blue is now, yellow is then, red is ancient, infrared is primordial, the universe is a time machine, and redshift is the dial. As we drift through this chapter, thinking of the stretching light, we can feel a sense of melancholy. The universe is flying apart. The connections are breaking. But there is also beauty in it. The expansion is what allows the universe to cool. It is what allows the sky to be dark so that life doesn't burn up. It is what gives us a future. If the universe were collapsing, the light would be blue-shifted. It would get more energetic. The radiation of the Big Bang would be compressed back into gamma rays. The sky would become a furnace. We need the redshift. We need the tired light. It is the condition for our existence. In the next chapter, we will confront the force that is driving this stretching. We will look at the engine of the expansion. We will stare into the face of dark energy. We will explore the vacuum energy of empty space. We will ask why the universe is pressing the accelerator pedal. We will see how this mysterious force, which makes up 70% of reality, will dictate the ultimate fate of everything. Will it tear the atoms apart? Or will it simply leave us in a cold, eternal isolation? For now, imagine the light waves passing through your room. Radio waves from distant quasars, stretched by billions of years of travel. They pass through your walls, through your body, silent and invisible. You are bathed in the stretched light of the cosmos. You are standing in the flow of the expanding river. Feel the space around you. It is not static. It is growing. Slowly, quietly, relentlessly. Rest in that expansion. Let your mind stretch with the light. We have followed the ancient photons on their 13 billion-year marathon across the cosmos. We have seen them stretched by the expansion of space, cooled from the blinding heat of the Big Bang into the gentle, invisible wash of microwaves. We know they are there, filling every cubic centimeter of the room you are in, passing through you like ghosts. But for a long time, knowing they were there was not enough. We wanted to see them. We wanted to capture them, not just as a static hiss in a radio antenna, but as an image. We wanted to take a photograph of the infant universe. To do this, we had to leave the Earth. The atmosphere of our planet, which protects us so well, is an obstacle to this ancient light. Water vapor in the air absorbs microwaves. To see the background light clearly, we had to rise above the weather. We had to build observatories in the cold silence of orbit. The first of these great cosmic cartographers was launched in 1989. It was called COBE, the Cosmic Background Explorer. Its mission was simple: to scan the entire sky and measure the temperature of the darkness. When the data first came back, it was shocking in its perfection. The scientists plotted the intensity of the light against its frequency. They were looking for a specific shape, a black-body curve. This is the signature of an object that glows purely because of its heat, in perfect thermal equilibrium. The points on the graph lined up exactly with the theoretical prediction. It was the most perfect black body ever measured in nature. It proved, beyond a shadow of a doubt, that the universe had once been in a state of hot, dense equilibrium. It was the final nail in the coffin of any theory that denied the Big Bang. The universe had a beginning, and it was hot. But COBE did something else. It looked for variations. It looked for the ripples. Remember, if the early universe had been perfectly smooth, gravity would have had no way to build galaxies. There would be no clumps to pull matter together. The universe would be a featureless soup forever. So, the scientists knew there had to be bumps, tiny deviations in temperature. They looked at the map COBE produced. At first, it looked smooth, but as they turned up the sensitivity, filtering out the noise of the galaxy and the solar system, a pattern emerged. It was a mottled landscape, blobs of blue and pink. The blue spots were colder than the average by 1 part in 100,000. The pink spots were warmer by the same tiny amount. These were the seeds, the primordial fluctuations. The blue spots were the slightly denser regions where gravity was already winning. The pink spots were the slightly emptier regions. We were looking at the embryonic skeleton of the cosmos. The image was blurry. COBE had poor vision, but it was enough. One scientist famously said, "If you're religious, it's like seeing the face of God." It was the blueprint of everything that would ever exist. But science is never satisfied. We needed a sharper image. In 2001, we launched WMAPI, the Wilkinson Microwave Anisotropy Probe, and in 2009, the European Space Agency launched Planck. Planck was a masterpiece of engineering. Its detectors were cooled to near absolute zero, so that their own heat wouldn't interfere with the cold light of the cosmos. It scanned the sky with a sensitivity that is hard to comprehend. It could detect a heat difference of a millionth of a degree. Attachment, attachment. The map that Planck produced is one of the most important documents in the history of humanity. It looks like a speckled egg, an oval of chaotic colors. But to a cosmologist, it is a book written in the language of physics. By analyzing the size and distribution of these speckles, we could decipher the recipe of the universe. This is the science of precision cosmology. Let us decode the map. The first thing we look at is the spots. How big are they? Are they mostly large blobs or tiny freckles? This analysis reveals the sound horizon. Recall the sound waves ringing through the early plasma, the baryon acoustic oscillations. Those waves could only travel a certain distance, before the universe froze at recombination. That distance is the sound horizon. We know exactly how big that distance should be in the early universe, about 450,000 light-years. It is a standard ruler. Now, we look at the map. We measure how big those spots appear to us on the sky today. They appear to be about 1 degree across, about twice the size of the full moon. This gives us a geometry lesson. We have a triangle. We know one side of the triangle, the physical size of the sound wave. We know the angle of the triangle, how big it looks from Earth. Using trigonometry, we can figure out the shape of the space the light traveled through. If space were curved like a sphere, closed universe, the light rays would converge, and the spots would look bigger than 1 degree. If space were curved like a saddle, open universe, the light rays would diverge, and the spots would look smaller. But the spots are exactly 1 degree. This means the light traveled in straight lines. The conclusion is profound. The universe is flat. This doesn't mean it is two-dimensional like a pancake. It means that the three-dimensional geometry of space obeys Euclidean rules. Parallel lines stay parallel. Triangles add up to 180 degrees. It suggests that the universe expands forever. It will not crunch back down. Next, we look at the intensity of the spots. This tells us what the universe is made of. The sound waves in the early universe were a battle between gravity, pulling in, and pressure, pushing out. The ordinary matter, the baryons, interacted with the light and felt the pressure. But the dark matter did not. It only felt gravity. This difference creates a distinctive pattern in the ripples. By measuring the height of the peaks in the data, we can weigh the universe. The data from Planck gave us the recipe with 3 decimal places of accuracy. Normal matter, atoms, stars, gas, US, makes up 4.9% of the universe. Dark matter, the invisible scaffolding, makes up 26.8%. And dark energy, the mysterious force driving the acceleration, makes up 68.3%. This is the lambda CDM model. It is the standard model of cosmology, and it comes almost entirely from staring at the static of the microwave background. Think about what this means. Everything we have ever seen with our eyes, every star, every galaxy, every planet, is less than 5% of reality. We are the foam on the ocean. The vast majority of the universe is dark. The map also tells us the age of the universe. By running the expansion movie backward, guided by the density numbers from the map, we arrive at a beginning, 13.8 billion years. Not 10, not 20, 13.8. We know the birthday of the cosmos better than we know the history of our own geological eras. But there are mysteries hidden in the map, too. Anomalies. There is a cold spot, a large region of the southern sky that is unexpectedly chilly. It is colder than statistics predict. Is it a supervoid? A vast emptiness a billion light-years across where no galaxies formed? Or is it the bruise left by a collision with another universe? There is the axis of evil. The patterns in the map seem to align in a weird way with the plane of our own solar system. This shouldn't be. The Big Bang happened everywhere. It shouldn't care about the orientation of the Earth. Is it a coincidence? Is it a mistake in the data processing? Or is the universe not as random as we think? These whispers keep cosmologists awake at night. But the overall picture is one of stunning consistency. The theory works. The Big Bang happened, The light was trapped, and then it was freed. As we contemplate this map, we are engaging in the ultimate act of archaeology. We are digging through the layers of time, not with shovels, but with antennas. The light from the surface of last scattering is the oldest thing you will ever interact with. The photons hitting the detector left their source long before the Earth existed. They have been flying through the dark for 3 times the age of the solar system. They have seen the universe grow up. They flew past the first stars as they ignited. They flew past the forming galaxies. They flew past the collision that created the sun. They are the witnesses of history. And they are still coming. The supply is endless. Every second, a new shell of the universe's history reaches us. We are constantly receiving the news of the beginning. But because of the expansion, the news is getting harder to read. The redshift continues. The microwaves are stretching into radio waves. In the far future, the wavelength will be as long as the galaxy itself. The background light will fade into undetectable noise. Civilizations of the distant future may not be able to see the CMB. They will look at the sky and see only darkness between the stars. They will assume the universe has always been dark. They will have no evidence of the fireball. We are lucky. We live in the time of the glow. We live in the era where the universe is still telling us its story. This light connects us to the unity of all things. The atoms in your body were there when this light was released. They were part of the plasma. The electrons in your blood once scattered these very photons. We were all inside the fog. When the fog lifted, the matter became us, and the light became the background. We are the 2 halves of the original fluid, reunited now by the act of observation. The astronomer Carl Sagan famously said, "We are made of star stuff. But we are also made of the Big Bang's light. We are the children of the flash." In the next and final chapter, we will rest in this realization. We will look at the universe not as a collection of objects, but as a quiet balance. We will explore the future of this light. As it stretches into infinity, does it lose its meaning? Or does it become the silent hum of eternity? We will reflect on the peace of deep time, the knowledge that the universe is unfolding exactly as it must. The expansion is not a tearing apart, it is a breathing out. For now, imagine the map of the sky, the blue and pink speckles, the fingerprint of creation. Imagine wrapping yourself in that blanket of ancient light. It is a cold light now, 2.7 degrees Kelvin, but it carries the memory of infinite heat. It surrounds the Earth. It surrounds the solar system. It surrounds the galaxy. It is the ocean in which we float. You are never in the dark. Even in the deepest cave, even in the blackest night, the microwave background is there. The universe is always glowing. You are always touching the beginning. Rest in that continuity. The story is unbroken. From the first second to this second, the light has held. We have traveled from the blinding, suffocating fog of the first moments to the clear, open skies of the modern cosmos. We have watched the universe hold its breath for 380,000 years, and we have seen the moment of release, the flash that lit up the dark. We have followed those photons as they stretched, cooled, and aged into the gentle microwave hum that surrounds us today. Now, we must look forward. The story of the cosmic background light is not over. It is still unfolding. the photons are still traveling, still stretching, still carrying the news of the creation to every corner of reality. But the universe is changing. The stage upon which this light travels is growing larger every second. As we learned in our journey through the expanding universe, the expansion is accelerating. Dark energy is pushing the galaxies apart. It is stretching the fabric of space faster and faster. This has a profound effect on the ancient light. Right now, the background light is in the microwave region of the spectrum. It has a wavelength of about 2 millimeters. It is cold, 2.7 Kelvin. But as the eons pass, the stretching will continue. The microwaves will be pulled apart. They will become radio waves. In a few billion years, the wavelength will be meters long, then kilometers, then light years. The energy of the photons will drop closer and closer to absolute zero. The hiss of the universe will become a silence. This leads to a melancholic realization. We are living in a privileged time. We live in the era of the observable Big Bang. We can look at the sky and see the fire of the beginning. It is dim and redshifted, but it is there. It is detectable. Attachment. But in the distant future, this will not be true. Imagine a civilization arising on a planet around a red dwarf star 100 billion years from now. Their astronomers will build telescopes. They will look at the sky. But they will not see the cosmic microwave background. By then, the light will have been stretched so thin, its energy so diluted, that it will be physically impossible to detect. The signal will have faded into the noise of the quantum vacuum. These future astronomers will look out and see a dark, empty universe. The distant galaxies will have been swept away by the expansion, moving faster than light, disappearing over the horizon. The evidence of the Big Bang will have been erased. They will likely conclude that their galaxy is the only thing in existence. They will think the universe is static, eternal, and lonely. They will have no way of knowing that it began in fire. They will have no way of knowing that we were here, witnessing the glory of the expansion. We are the keepers of the memory. We are the witnesses. It is our duty to record the story of the light, to carve it into stone or silicon, so that perhaps in the deep future someone might find it and know that the universe was once bright. But let us return to the present. Let us return to the light that is touching us now. This light connects us to the unity of all things in a way that nothing else can. Think about the atoms in your body, the calcium in your bones, the iron in your blood, the carbon in your breath. Where were they when the cosmic background light was released? They were there. They were part of the fog. Before the light broke free, the matter and the energy were one fluid. The electrons in your fingertips were bouncing off the photons that now make up the background static. Your substance and the universe's light were dancing together in a tight, hot embrace. We were all inside the fireball. We were not observers then. We were participants. When the fog lifted, the two halves of reality separated. The matter collapsed to form stars, planets, and people. The light flew off to fill the void. We went our separate ways. But now, 13 billion years later, we are reunited. The light that left us then is returning to us now. It arrives from the edge of the universe to touch the matter it once held. It is a cosmic reunion happening every second of every day. When you stand under the night sky, You are being bathed in the echo of your own origin. The photons hitting your skin are the long-lost siblings of the atoms in your skin. The astronomer Carl Sagan famously said, "We are made of star stuff." And that is true. Our heavy elements were forged in stellar cores. But we are also made of the Big Bang's light. We are the children of the flash. The energy that animates us is just a different form of the energy that glows in the microwave sky. There is a profound peace in this realization. It dissolves the feeling of isolation. We often feel small and separate from the universe, tiny specks on a rock, surrounded by alien emptiness. But the background light reminds us that there is no separation. The space between the stars is not empty. It is full. It is full of the oldest thing there is. We are swimming in an ocean of connection. The static on the radio is the sound of the universe breathing. It is the Om of creation. It has been humming since the beginning, and it will hum until the end. So, what is the future of this light? As it stretches into radio waves, and then into wavelengths as long as the universe itself, does it disappear? Energy cannot be destroyed. It can only change form. As the photons lose energy to the expansion, that energy goes into the fabric of space-time. It pays the cost of the growth. The light sacrifices itself to make the universe bigger. In the far, far future, the dark era, the stars will have burned out. The galaxies will have evaporated. Black holes will have decayed. The universe will be a sea of cold photons and neutrinos, spread so thin that they never interact. This is the heat death. It sounds tragic, a cold, lonely end. But in the language of physics, it is equilibrium. It is the state of maximum rest. The universe began in a state of maximum tension, infinite density, infinite pressure. It has spent its entire life relaxing, uncoiling, exhaling. The heat death is the final deep breath out. It is the ultimate peace. But we are not there yet. We are here in the vibrant middle. We are in the stelliferous era, the age of stars. The universe is awake, and it is beautiful. We have the eyes to see the starlight, and the instruments to detect the ancient light. We have the minds to reconstruct the story. As you lie in bed tonight, imagine the room around you. It is dark to your eyes, but to the universe, it is glowing. The walls are transparent to microwaves. The ceiling is glass. The cosmic background light is streaming down through the roof, passing through your blankets, passing through you. 400 million ancient photons are occupying the space of your body right now. They are passing through the empty spaces between your atoms. You are glowing with the light of the Big Bang. You are never in the dark, even in the deepest cave, even in the blackest night. The microwave background is there. The universe is always luminous. You are always touching the beginning. The timeline is not a straight line that leaves the past behind. It is a field that surrounds you. The beginning is here. Rest in that continuity. The story is unbroken. From the first second to the second, the light has held. Feel the gravity of the earth holding you safe. Feel the warmth of your body, energy that has traveled through time to become you. Feel the quiet hum of the air. Let your thoughts drift back to the fog, the warm orange mist, the safety of the plasma. Then let yourself drift forward to the clearing, the release, the flight. You are flying through the void, weightless and free. You are light. You are traveling across the eons without effort, without time. There is no rush. The universe has billions of years. You have all night. Let the expansion carry you. Let the redshift slow you down. Let the energy fade into a gentle, long wave of sleep. May your rest be as deep as the cosmos, and your dreams as bright as the first light. Good night.